Okay, so section 22.5 has to do with isomerism in coordination compounds. And coordination compounds will exhibit both structural and stereoisomerism. Just as a reminder, structural isomers are those which have different bonding partners. So, atom A will be bonded to atom B in one isomer, but it'll be bonded to atom C in another isomer. And then stereoisomers, all of the atoms have the same bonding partners, but there's something else about their three-dimensional shape which is different. That involved cis-trans isomers and optical isomers for organic compounds. Anyway, so for coordination chemistry, we're going to see much the same sorts of isomerism. Structural isomers will be divided into coordination isomers and linkage isomers. We'll talk about them individually. And then the stereoisomers will also have cis-trans and optical isomerism. And so we'll walk through these all one by one. Coordination isomers are isomers which will exchange elements between the primary and the secondary coordination sphere. So consider this compound. I'm sorry, that's a cobalt, not a carbon monoxide, a lowercase o. CONH3 5 BrCl and CONH3 5Cl Br. So they contain all of the same atoms, but in the top case, the bromine atom is covalently bonded to the cobalt. And the chloride ion is just nearby in order to preserve charge balance. If you were to boil away all of the solvent, then they would form an ionic compound where everything inside the bracket is actually one giant polyatomic cation, and then the chloride would be an anion. In solution, the bromine is covalently bonded and the chloride is just elsewhere in the solution. And then here we've got the case where the chlorine is covalently bonded to the cobalt and the bromide ion is just there to balance with a negative charge. So these are coordination isomers. They contain the same atoms, but they're forming different sorts of bonds. So a bromine dative bond to the cobalt here, or a chlorine dative bond to the cobalt there. So those are coordination isomers. And I want to point out your textbook has a little bit of an error with the ammonia, a typo, where they say NH5 instead of NH3,5. So what I've written up here is correct. The textbook is wrong. Okay, the next is a linkage isomer. Okay. That's a lowercase k, sorry. So linkage isomers are going to connect ligands through different donor atoms. We saw that some of the ligands are multidentate and have multiple donor atoms that can simultaneously coordinate with the metal cation. But a few of them have multiple donor atoms, but they're still monodentate ligands. And so only one of those atoms can actually form a dative bond at a time. And so that gives the opportunity for linkage isomers. So consider the thiocyanate ion. Usually we'll write it like this, SCN minus. The thiocyanate ion has lone pairs on both the sulfur and the nitrogen, and it's actually able to form bonds through either one of those. So we would write a coordination compound like this. Okay, so this is a palladium. It's got a coordination number of 4. It's got 4 different ligands, 2 ammonias or 2 amines, 1 chloride, and then 1 thiocyanate. And the thiocyanate is in parentheses just like the NH3 is in parentheses. Not because we have more than one of them, but just to show that they are grouped together as one ligand. Okay, so this is one linkage isomer, and then the other one would be palladium NH3 2 Cl NCS. So the compound on the top has the thiocyanate ion bonding through the sulfur as donor atom. The compound on the bottom has the thiocyanate ion bonding through nitrogen as a donor atom. So this is an example of a linkage isomer. And it also kind of explains why we write thiocyanate in this way. When we were doing Lewis structures and things, if you were in my class anyway, I believe I did address this very briefly. Usually you write the least electronegative atom first, so this would have been something like CSN or CNS if you followed that convention, but we're just so used to being mindful about whether thiocyanate is binding through the sulfur or through the nitrogen that it just seems more natural to write it in this way. So SCN bonds through the S, NCS bonds through the N. Those are linkage isomers. And those are the 2 types of structural isomers, where you actually have different atoms forming bonds with different bonding partners. The next, we'll go into stereoisomers, and the first kind is a cis-trans isomer. And so we just talked about cis-trans isomers not long ago. You know, this would be a cis 1,2-dichloroethene, where the substituent groups are on the same side of the double bond. Well, there are no double bonds in coordination chemistry, and so cis-trans isomerism looks a little bit different, but it still follows that same basic idea. There is something that is preventing free rotation, and so it creates this sort of 3-dimensional directionality of the bonds. They're either on the same side or on the opposite side. Anyway, let me just jump ahead to the figure. Oops, I passed it. Okay. So here we have platinum bonded to 2 amine groups and 2 chloro groups. And it's in a square planar configuration. And so what you see here on the screen is a pretty good representation of the actual shape in 3-dimensional space. 90-degree angles, and you could have the 2 chlorines on the same side as the platinum. That would be cisplatin. Or you could have the chlorines on opposite sides, and that would be transplatin. So you may have heard of cisplatin as an anti-cancer drug. What cisplatin will do is those 2 chlorine ligands that are on the same side of the cisplatin complex are going to bind themselves to DNA and prevent it from replicating properly, and that's going to make it effective at killing cancerous cells. All chemotherapy is fairly indiscriminate about how it kills the cells, but the cells which divide more rapidly are going to be killed more rapidly because it's the dividing which makes them vulnerable to this DNA binding attack that cisplatin it does. So anyway, transplatin looks very much similar to cisplatin, but it is ineffective as an anti-cancer drug because you need both of those chlorines on the same side in order to form the proper bonds with the DNA. And so that is cis-trans isomerism. Since you may have heard of cisplatin, I think it's a great example to help you remember how cis-trans isomerism works. And then finally, let me get rid of this. There can be optical isomers. And so you may remember optical isomers are isomers where the mirror image of a molecule is not superimposable on itself. We use the example of hands. My right hand is a mirror image of my left hand, and they look to be structured in the same way, the thumb next to the pointer and the palm on the opposite of the back of the hand, and all that is the same, whether you're talking about the right or the left hand. They're mirror images, and yet I cannot put my right thumb over my left thumb and my right finger over my left finger. I can't superimpose them. I'll either have palm to back and back to palm, or I'll have pinky to thumb and thumb to pinky. It just doesn't work. If I try to put a right glove on my left hand, it doesn't work. Anyway, the easiest way to find optical isomers in organic molecules is to look for a bonding center that has 4 distinct groups bonded to it. Well, for our coordination compounds, there are tetrahedral coordination compound geometries. And so if you have 4 unique ligands all bound to the central central metal cation in a tetrahedral geometry, then that could be a chiral center. But I wanted to show this figure from the textbook. This is cobalt with 3 ethylene bidentate ligands, and because of the way that those bidentate ligands sort of create these bridges in 3-dimensional space. Anyway, it's kind of analogous to protein and DNA helixes, which are also chiral. I gave the example of a staircase, spiral staircase, which is chiral. Well, in much the same way, this compound here is chiral, so it exhibits optical isomerism. And it would be a lot harder for you to identify whether one of these compounds is chiral without having the model in front of you or something like that. But I wanted to include it just because optical isomerism is really a very general concept, and it can sometimes appear in surprising places and surprising ways. So that's it for 22.5.